All right, now we're going to take a look at discontinuities. So with discontinuities, we are going to be looking at where graphs break. And so let me pull up a graph here, and I'm just going to do a blank graph. There's no special symbols here. And I don't have a discontinuity graph, at least not yet. I haven't thought through if I even wanted to do one or how I would do it. But so I'm just going to graph this in a normal blank graph. F of x equals division line x cubed minus 9x over x plus c minus 7. So I've typed it in exactly as they've shown, and it says what value of c has an infinite discontinuity, and there's going to be answer choices. Let me pause this and grab the answer choices. Okay, now I got some answer choices here. And it says a function is shown for which of these values does the graph have an infinite discontinuity. And so what we're going to do is we're just going to look at the different values and see which one's correct. If c is a -3, if c is a -3, question for you, do we have a infinite discontinuity? I'm going to zoom way out. Do you see any breaks there if c is a -3? Remember, infinite, and I could go this way. Infinite means it breaks and goes to negative infinity. So I don't see any there. Inside lies, so it actually would be a bit +3. Where is it? There it is. Does that look like an infinite break, a jump break, or a removable break?
Infinite break.
Oh, I'm hearing all of them. So infinite's where the graph goes to infinity at that spot. So I'm on the spot. Remember, inside lies. Since that's inside, it's going to lie. So I'm actually at +3. Let me do this. Let me copy this and turn the second one into a table. There we go. And so you can see this. The value -3 is a number, but the value +3 is undefined. That's because inside lies. So it is undefined at 3. The question is, does the graph go to infinity at 3? Or what does it actually do at 3? Does it jump apart, or is it just a removable break? What do we have there? So I'm not hearing much. What type of break is that? When it's just a little open circle. Do we call that infinite, jump, or removable? That's a removable break. This is a removable discontinuity. And I'll show you why in a second. I'll show you the algebra, but that's removable. Now it says try 0. So I'm going to slide C to make it be a 0 here. At 0, what type of break is that? Again. And you can kind of see which one's going to be different here in a second than the others. So that's why I'm doing this graph, so you can see the one belongs, one does not. I'll now make C become a 3. This will make it easier if I just do this by 1. There we go. Okay, C is now a 3, which means, because inside lies, it's going to be occurring at -3. So if I go to -3, what type of break does this look like at -3? There it is. What type of break is that? Again, it's a removable. Removable, removable, removable. So that means 9 better be the answer here. Let's see, what happens if I change this to a 9? So zoom out so you can see, where is 9? Oh wait, inside lies, it's on the other side of the graph. If I zoom out, you'll see that this graph is totally separate at 9. At 9, this graph breaks and goes to infinity. Let me do it this way. Let me change my settings to where it goes really low and really high, but it doesn't get very far apart. Since I'm looking at 9, I'm going to just go 15 to 15. There we go. As you can see, when I zoom this out, this graph, it's totally different at 9. You see how it's broken apart in 2 separate pieces? That's an infinite discontinuity. So 9 is the correct answer here. Now, mathematically, what's different on these? Well, if you factor the top, so remember how you do this algebraically, I did this earlier today, is you factor these. I have a GCF up in the numerator here. So I could actually factor out what's shared in the numerator. An x. If I factor out the x, I'm left with x squared minus 9. Like that. And this x squared minus 9 is what we call a difference of common squares. Difference of squares. Difference of squares. You could x method this, but what you would get is if you factored this again, you'd end up with x times x minus 3 times x plus 3 over x plus c. So this is the algebra I'm showing you right now. So why do these all get removed? Is because if x is a 0, it makes, if c is a 0, you have x plus 0, which is nothing, and you can cancel these x's out. That's why that one's removable. If c were a negative 3, now this one cancels with that one, and it would become removable. If c were a positive 3, now this cancels with this one. And so that's why those are removable. Whereas if x is 9, if c is 9, there's nothing for it to cancel out with. Even up here, if I put a c of 9, these two are not identical. They cannot be canceled. So for that reason, this would be an infinite discontinuity because you cannot divide by 0 and it never cancels. So that's why it's an infinite discontinuity there. I think graphing is the way to go, but you just need to be looking at it. And I think our participation just went down on that problem. So let's be participating a little bit more. All right. Here's another one. Polly is given this function. What discontinuities did Polly discover upon her investigation? So again, I'm going to pause this and I'm going to go get the answer choices here. Okay, so here's the problem. And we want to know about the discontinuity. So what I'm going to do is I'm going to change this problem to the new equation. So I'll delete that. I'm going to type in this new equation. X plus 3 over x squared plus x minus 6 plus 4. And the problem asks us to find, or it gives us some values. And so here's the cheating way with multiple choice, is to only observe these values. We're going to look at the x values 2, negative 3. I'm going to make a list here. The x's we need to check out. We're going to have x values of 2 and negative 3, negative 3 and 2, 4, and 0. We're going to go check out those values and see what happens at those spots. So I'm going to make sure they're in my table. So I have a negative 3, I have a 2, I need a 0, and I need a 4. So on the table, I'm adding all these points. Which ones are undefined? Look at my table here. 2 and negative 3 are the undefined values. So my answer must include 2 and negative 3. It cannot include 4 and 0 because those are not undefined. So I'm going to eliminate this answer choice and this answer choice. So now it's 50-50. And now I just look at, okay, what happens at 2 and 3? I have what type of break is this if the graph breaks and goes up to positive infinity and down to negative infinity? What do you call that type of break? Nope, I'll say it again. Think of my words. What do you call a break that goes up to positive infinity and down to negative infinity? Infinite. Yeah, it's an infinite break. So the infinite occurs at 2. You see how that's at 2? Zoom in. That's at 2. So the infinite is at 2, which means this is the correct answer here. This first one is correct. It says removable at negative 3. When I go to negative 3, removable should look like an open circle. Notice my picture here. It looks like an open circle. So for that reason, that would be removable. Yep. So a jump, that's piecewise, if you remember. Piecewise is where, let me just give you a jump. Let me go backwards. This graph had a jump discontinuity. Jump is where it jumps apart, like that. This is not jumping apart. These are going to infinities, so you call it infinite. So jump, you can like literally count how far they jump from one spot to another. Let me give you another one we saw earlier today. Here, what do you call this one? From this spot to this spot. These would be infinite because these are going to infinities. That break between these two pieces is an infinite. This one right here is a jump because it's jumping from this place to this place. This one, the graph's not jumping from one place to another, but it's missing a little spot. A little spot's been removed. So you call that one removable. Removable, jump. This is infinite, that break, because the graph's going to infinity. Okay, and let's see here if I got another one, or if that's it. Yes, I got two more. What statement most accurately describes the discontinuities in this graph? This has a weird symbol. How do I graph that? Yeah. Piecewise, very good. Use this one, piecewise. So f of x, or f1 here on piecewise, f1 refers to the top piece here. This is kind of what I'm going to do is I'm going to call this f1 right here on the left, and this is going to be restriction 1. And down here, this is going to be f2, and this is going to be restriction 2. That's how I'm going to graph these. And so when I go to f1, I type in the top, which is 2x squared plus 3x minus 2 over x plus 2. The restriction is x is less than 1. So that's the restriction, that's the graph. There's the first piece. Second piece, I have negative x squared plus 2. And it's x is greater than or equal, so just put the equal sign, 1. So here's our picture. And I could look for statements, but is that broken apart? Would you say that's discontinuous, or is that continuous there if it's closed dots? It's continuous. I do think there is one break somewhere. Oh, here, I'm missing spot. It's not letting me click it. Oh, down here. Where's the break at? Negative 2. There is a break at negative 2. And if you can't see the break, what do you call it if you can't see it? Is it an infinite, removable, or jump? Infinite. Infinite, you can always see. It goes to infinity. Which one is it that you can't see unless you click the exact spot? Jump. No, jump you can see. What's the last one? Removable. That's a removable. This has a removable. Discontinuity at x equals 2. Again, what I would encourage you though, if you're doing multiple choice, is to look at the answer choices. Oops, wrong one. Oh, this doesn't even say the spot. I'm going to say look at the spot. But this graph has a removable. How do I know? It's because it says undefined. That means there is a break. And the graph broke at negative 2, I'm sorry, negative 2. Okay, I have one more, and then I'm going to give you your DOL. So it says, which function has a removable discontinuity? There. Actually, you know what I'm going to do? I'm going to pause, and I'll let you graph these and see which one you think has a removable at x equals 2. So you know where to test on the graph. You know where to look. So graph these and see which one's different at x equals 2. All right, we're going to see which one's different now. So I'm going to graph this as piecewise. 3x minus 1, and x is less than, or I'm going to hit the equal sign, equal to 2. The other problem is x squared with x greater than, so I'll delete, and I'll make that equal to sign go away. 2 this way. At 2, do we call that a removable? When you look at my picture, is that a removable? So removable, this one more time, you cannot see it right away. Removable, you will not be able to see right away. You'll have to click it to see it. Can you see a break there? Yes, you can see a break. So what type of break is this one?
Jump.
It's a jump. This is a jump because you can see it right away. A removable, let me write them out here. A removable looks like this. That's removable. You won't see it right away on Desmos, you have to click it. A jump, wow, let me try that again. A jump is something like this. And then an infinite is something like this. Like that. Okay, so infinites go to infinity. Jump, the graph just picks up, you move your pencil somewhere else and keep on going. Removable, it's almost like you just barely pick up your pencil for a second, put it right back down in the same spot and keep going. Okay, so this is a jump. So this one's not it. F is gone. Okay, so now I'm going to try the next one. Because none of those are piecewise, I'm just going to delete the crazy letters here and get a clean graph. F of x equals x minus 2, forget the division sign, over x squared minus 9. And what we can do is change this to a table, and you can just, we want to look at the value at 2. So I'm not only concerned with 2. And so we delete all that. I'm only concerned with 2. It's not even broken at 2. This graph is not broken. So it's not this one. This is continuous at 2. It's not that one. So now I try this next one. X squared plus 2x over x squared minus 4. Okay, this one's broken. So we're in good business there. It's broken. What type of break is occurring though at 2? That's infinite. Is it supposed to be infinite?
No.
Okay, so it looks like J is going to be the correct answer here. Minus 8 over x squared minus 2x. Right there. Okay, so 2, again, it's broken. But when I look at the graph, do you see a break? At 2. You're only looking at the x value 2. Let me zoom in. The x value 2, do you see a break right there? No, if it looks together, but the table's saying it's broken, then it's removable. When I click it, you'll see it's going to go to that white circle. You have to click it. So this one is, J is the removable option. All right, so now you have DOL to finish up the lesson, and then after that, we'll pick up next class.
There's an Alex for this lesson too?
Hang on a second.